today we are going to study about some bond parameters. Is it clear? That is, bond parameters means every covalent bond is characterized by a set of bond parameters. Okay, every covalent bond is characterized by a set of bond parameters, and the first one in that is bond enthalpy. Children, you must have studied about the term enthalpy in third chapter, that is in periodicity. Okay, so here we can say that the bond enthalpy means it is the energy needed particularly for making or breaking of bond. Okay, generally we can say that either the energy will be released or energy will be absorbed during this process, bond formation and bond breaking. So the energy required in the breaking or making of bond is generally termed as bond enthalpy. Or we can say that it is the energy, it is the enthalpy required to break 1 mole of a bond of a type. Okay, whatever be the energy required to break 1 mole of a bond of a same type so as to separate the bonded atoms in the gaseous state. Suppose if you consider CH4. So whatever be the energy required to break this particular bond, that we just consider it as bond enthalpy. Is it clear, children? So bond enthalpy is defined as the energy required to break 1 mole of a bond of same type so as to separate the bonded atoms in gaseous state. Is it clear? I will repeat it once more. It is the energy required for what purpose? In order to break 1 mole of a bond of same type so as to separate the bonded atoms in gaseous state. Now there are certain factors which control this bond enthalpy, and the first one we can consider it as size of atoms. First factor which control bond enthalpy is size of atom. Children, if you just consider 2 hydrogen atoms. Okay, you know that hydrogen is the first element in the periodic table. So, and then you consider 2 any other, for example, you consider there is 2 atoms of chlorine. Obviously, chlorine atomic number is 17, so the size of chlorine is slightly bigger than that of sorry. We can consider it will be comparatively bigger compared to that of hydrogen. So here, as the size of the atom increases, we can say that it will be easier to break the bond. Okay, so bond enthalpy decreases with the increase in size. Is it clear? As the size of the atom, why it is so? As the size of the atom increases, the extent of overlapping decreases. Is it clear? Therefore, bond enthalpy decreases. Is it clear? So, bond enthalpy in a way it is indirectly proportional to size. As size of atom increases, bond enthalpy decreases due to lesser extent of overlapping. Okay. Next factor, let us consider it as multiplicity of the bond. Multiplicity means that is again you have studied about single bond, double bond, triple bond. So here we can say that as the number of bonds increases, that is suppose you just consider C single bond C, C double bond C and C triple bond C. You can see that between the first case C single bond C means only a pair of electrons are involved. In case of C double bond C, 2 pairs of electrons are involved, and in C triple bond C, 3 pairs are involved. As the number of shared pair of electrons increases, obviously the attractive force between 2 atoms increases, and hence bond enthalpy also increases. Is it clear? So as multiplicity of bond increases, bond enthalpy increases. What is the reason behind this? It is due to the increase in the number of shared pair of electrons, which in turn increases the magnitude of attractive force. Is it clear, children? As the multiplicity of the bond increases, number of shared pair of electron increases, and hence the bond enthalpy increases. Now the third factor, let us consider number of lone pair of electrons. Bond enthalpy also depends on number of lone pair of electrons. About those children, yesterday also we have studied. You know that as the number of lone pair of electrons increases, the repulsive interaction increases. Repulsive interaction increases means it is easy to break the bond. So obviously bond enthalpy decreases. Is it clear? So bond enthalpy, we have seen that it is the energy required to break one mole of a particular type of bond so as to separate them in the gaseous state. And it depends on three factors, that is size of atom, multiplicity of bonds, as well as number of lone pair of electrons. Is it clear, children? The first bond parameter, that is bond enthalpy. Now let us consider the second bond parameter, that is bond length. Second one we are going to study is bond length. As the same term indicates, bond length means it is the distance between. It is defined as the distance between two bonded atoms. Distance between the centers of two bonded atoms in a molecule. Okay, bond length is defined as the distance between, that is the average length between the centers of two bonded atoms in a molecule is termed as bond length. Is it clear, children? If you just consider that is one particular molecule, what about this distance? That is distance between, average distance between the centers of two bonded atoms in a molecule is termed as bond length. Is it clear? Again, we can say that it is defined as the average distance between the centers of two bonded atoms in a molecule. If you consider an ionic crystal, ionic compound, we can say that sum of the ionic radii of, that is in case of an ionic compound, bond length, we can say that it is equals to sum of ionic radii of cation plus ionic radii of anion. That is termed as bond length. Or in case of a covalent molecule, it is the distance between the centers of two atoms in the molecule. Is it clear? So bond length is defined as average distance between the centers of two bonded atoms in a molecule. Bond length also depends on two factors. The first one we can consider it as size of atom. In this case, again you consider two small atoms or a molecule and two bigger atoms which form a molecule. You see from this figure it is very clear that as the size of atom increases, bond length increases. Is it clear? The bond length is directly proportional to size of atom. As size of atom increases, bond length increases. Second factor we can consider multiplicity of the bond. Multiplicity of the bonds. Again, children, you know that multiplicity increases means that is the number of shared pair of electrons increases. When the number of shared pair of electrons increases, magnitude of attractive force increases and hence bond length decreases. Is it clear? So bond length is defined as the average distance between the centers of the nuclei of two bonded atoms in a molecule. It depends on size of atom as well as multiplicity of bond. And as the size of atom increases, bond length increases, and with the multiplicity, as the multiplicity of the bond increases, bond length decreases due to the increase in magnitude of force of attraction. Is it clear? Now the third bond parameter we can consider bond angle. Third one is bond angle. Bond angle is defined as the average angle. Okay, it is the average angle between the lines representing the orbitals containing the bonding electrons. It is defined as the average angle between the lines representing the orbitals containing the bonding electrons. Is it clear? It is defined as the average angle between the lines representing the orbitals containing bonding electrons. That is the definition for bond angle. So bond angle is defined as the average angle between the lines representing the orbitals containing bonding electrodes. Suppose if you consider if the structure of the molecule is tetrahedral. In this case, we can say that the bond angle is coming around 109 degree 28 minutes. Or if it consider that is a triangular planar structure, we can see that the bond angle is around 120 degree. So the angle between the lines representing the orbitals containing the bonding electron is termed as bond angle. Is it clear? So the three bonding parameters in case of a covalent bond are bond enthalpy, bond length and bond angle. Okay children, today we are going to study a new topic, that is hybridization. Children, in lower classes in bio you must have heard the term hybrid. Okay, the same thing here we are going to study. Now just you consider any two orbitals. For example, you consider s orbital is going to combine with the p orbital. You can see that the shape of s orbital and p orbital is completely different. When these two orbitals overlap each other, you will be getting two other orbitals. That is, this is first one and this is the other one. This is two different orbitals. They neither look like s orbital nor like p orbital. This particular process is termed as hybridization. Is it clear? Hybridization means it is the process of intermixing of two or more orbitals. It is the process of intermixing of two or more orbitals to produce equal number of orbitals. Okay, if two orbitals undergoes hybridization, as a result of this process, you will be getting two orbitals as the product also. And what is the specialty of these orbitals? The orbitals which undergoes hybridization should be differ in their shape. Just say s orbital and p orbital, you know that they are completely different in their shape, and their energy will be almost the same. A slight difference in energy can also be there. Okay, it is the specialty of orbitals. We have seen that the orbitals which undergoes hybridization should differ in their energy as well as shape. And after hybridization, you will get equal number of orbitals which have identical shape as well as their energy will also be the same. Is it clear? So hybridization means it is the process of intermixing of orbitals which shows difference in shape and slightly different energy to get equal number of hybrid orbitals which possesses same energy and shape. Okay, so it is the process of intermixing of orbital. It is the process of intermixing of orbitals. And what are the specialties of orbitals? Orbitals should have different shape. Their shape should be different and they should be slightly differ in their energy. Shape and slight difference in energy. Why beta we are using the term slight difference in energy? Slight difference means, suppose if you just consider 2s orbital. 2s orbital is not able to combine or undergoes hybridization with 3d orbital. Is it clear? They will be showing so much lot of difference in their energy. So if it is 2s orbital, it should undergo hybridization with 2p orbital. That is why slight difference in energy. Okay, and as a result of this process, what you will get? You will get hybrid orbitals. The specialty of hybrid orbitals is that hybrid orbitals will have same energy. They possess same energy as well as their shape will also be same. Okay, this is what is same shape. This is what is termed as hybridization. So hybridization means it is the process of intermixing of orbitals which possesses different shape and slight difference in energy to get equal number of orbitals which possesses same energy and shape. Okay, now we have to study about different types of hybridization. In that, the first one, let us consider Sp3 hybridization. Sp3 hybridization. mixing of one s orbital. Okay, one s orbital is going to mix with 3 p orbital. Is it clear? One s orbital is going to mix with the 3 p orbital, and as a result of this process, you will be getting 4 sp3 hybrid orbitals. Is it clear? Sp3 hybridization means it is the process of mixing of one s orbital with 3 p orbital to form 4 sp3 hybrid orbitals. Okay, here we can see that the ratio of sp3 hybridization, the ratio between s and p character means it is 1:3. Or we can say that S character is 25% and P character is 75% in this hybridization. Okay, so sp3 hybridization means it is the process of intermixing of one s orbital with 3 p orbitals to form 4 sp3 hybrid orbitals. sp3 hybrid orbitals means, in this case, let us represent the same thing diagrammatically. Here it involves the intermixing of one s orbital. S orbital, you know that you have studied about the shapes of orbital in second chapter, that is structure of atom. So you know s orbital is spherical in shape. It undergoes hybridization with 3 p orbital. Let us consider all the 3 p orbitals, that is py, px and pz. Okay, it undergoes hybridization, and as a result of this process, you will be getting 4 sp3 hybrid orbitals. Okay children, you are getting here 4 sp3 hybrid orbital. So this process is termed as sp3 hybridization. It is the process of intermixing of one s orbital with 3 p orbitals and produces 4 sp3 hybrid orbital is termed as sp3 hybridization. Here you can see that the geometry of the molecule is tetrahedral. It possesses a tetrahedral structure with a bond angle of 109 degree 28 minutes. Is it clear? So sp3 hybridization is the process of mixing of one s orbital with 3 p orbitals and produces 4 sp3 hybrid orbitals. In this case, the structure, the geometry of the molecule is tetrahedral with a bond angle of 109 degree 28 minutes. Now let us see some examples for sp3 hybridization. First, let us consider the formation of methane. Example, let us consider the formation of methane. So the central atom undergoes hybridization. In this case, the central atom is carbon. Carbon, the electronic configuration, you know that it is 1s2, 2s2, 2px1 and y1. Okay, this is the ground state configuration of carbon. Ground state configuration of carbon is 1s2, 2s2, 2px1 and 2py1. Now we can consider in the excited state. Okay, in the excited state, the carbon will be exciting, or one electron from 2s orbital will jump to the next p orbital, that is pz orbital, which is vacant. Okay, so the configuration becomes 1s2, 2s1, 2px1, y1 and z1. Okay, the ground state configuration, here we can say that the ground state configuration of carbon is 1s2, 2s2, 2px1, 2py1 and 2pz0. In the excited state, one electron from s orbital get excited to pz orbital and it results in the formation of the configuration 1s2, 2s1, 2px1, 2py1 and 2pz1. Now let us see here. One s orbital undergoes hybridization with 3 p orbital. All of them are half filled. So one s orbital undergoes hybridization with 3 p orbital. Okay, So it undergoes hybridization with 3 p orbital and produces 4 sp3 hybrid orbitals. Okay, here you can see that it produces 4 sp3 hybrid orbital, and obviously the structure is tetrahedron with a bond angle of 109 degree 28 minutes. Is it clear? And here what we have seen, carbon in the excited state, the configuration is 2s1, 2px1, y1 and z1. So one s orbital undergoes hybridization with 3 p orbitals and produces 4 sp3 hybrid orbitals. Now you can see that in the molecule the next atom is, the neighboring atom is hydrogen. So this sp3 hybrid orbital of carbon combines with 1s orbital of hydrogen. 1s orbital means it is spherical in shape and it produces 4 sigma bond. Is it clear? The sp3 hybrid orbital of carbon undergoes sigma bond with 1s orbital of hydrogen and results in the formation of the compound CH4. Is it clear, children, about sp3 hybridization in case of methane? Okay. Let us continue with sp3 hybridization. In last period we have seen one example in case of sp3 hybridization, that is the formation of methane. Now let us consider another example, that is formation of ammonia. In case of ammonia, you know that the central atom is nitrogen. The electronic configuration of nitrogen, it possesses 7 electrons. So will you please let me know the electronic configuration of nitrogen? Yes, it is 1s2, 2s2, 2p, x1, y1 and z1. Children, you must be knowing, why we are writing it like this. Do you remember Hund's rule, which you have studied in 2nd chapter? Okay, so the configuration of nitrogen is 1s2, 2s2, 2p, x1, y1 and z1. Now here what happened? 1s electron, 1s orbital undergoes hybridization with 3p orbitals. So 1s orbital undergoes hybridization with 3 p orbitals and results in the formation of 4 sp3 hybrid orbitals. Okay, 1s orbital undergoes hybridization with 3 p orbitals and produces 4 sp3 hybrid orbitals. Okay, children. But here that means the structure of the molecule should be tetrahedron. Now what happened? In this case, you know that you can see the presence of only 3 hydrogen atoms. So this hydrogen, 1s orbital of each hydrogen undergoes overlapping, or it forms sigma bond with sp3 hybrid orbital of nitrogen. Okay, so you are getting 3 sigma bond here. It forms 3 sigma bond. But there is one lone pair of electrons there. Okay, you can see the presence of a lone pair of electron. And just recall VSEPR theory what we studied yesterday. So there we have seen that lone pair bond pair repulsion is stronger than bond pair repulsion. So in ammonia we have seen the presence of a lone pair of electrons. These electrons are not involved in bonding. Okay, due to the presence of this lone pair of electron in ammonia, you can see the presence of lone pair bond pair repulsion as well as bond pair repulsion. And which one is stronger here? The repulsive interaction or lone pair bond pair repulsion is stronger than lone pair bond pair repulsion is stronger than bond pair repulsion. So what happened? The structure of ammonia, you can see that instead of tetrahedron, it will be getting a pyramidal structure. Is it clear? So, and yesterday last class we have seen that in case of tetrahedron structure or in case of sp3 hybridization, the bond angle is 109 degree 28 minutes. But here in case of ammonia, it becomes 107 degree. Is it clear why the exception is there? So let me explain it once more. The configuration of nitrogen is 1s2, 2s2, 2px1, y1 and z1. So one s orbital of nitrogen undergoes hybridization with 3 p orbitals and it produces 4 sp3 hybrid orbital. According to the rule, the structure should be tetrahedron with a bond angle of 109 degree 28 minutes. But what happened here? We can see that in ammonia only 3 hydrogen atoms are there. So this sp3 hybrid orbital forms sigma bond with 1s orbital of 3 hydrogen atom. So we can see the presence of a lone pair of electrons, and according to VSEPR theory, lone pair bond pair repulsion is stronger than bond pair repulsion. Therefore, the structure of ammonia becomes pyramidal with a bond angle of 107 degree. Okay. Now let us consider one more example in case of sp3 hybridization. Let us explain the formation of water. Okay. Water, you know which is the central atom here? Yes, it is oxygen. So the configuration of oxygen, the atomic number of oxygen is 8. So the configuration is 1s2, 2s2, 2px2, y1 and z1. Okay. Again we can say that one s orbital of oxygen undergoes hybridization with 3 p orbitals, that is px, py and pz. Okay, it undergoes hybridization with 3 p orbitals and we can see that it produces 4 sp3 hybrid orbitals. Again you will be getting 4 sp3 hybrid orbitals. Okay, so according to the condition, the structure should be tetrahedron with a bond angle of 104 degree and 109 degree 28 minutes. Okay, that is what the theory states. But children, listen here, it undergoes hybridization and produces 4 sp3 hybrid orbital. In the formation of water, only 2 hydrogen atoms are there. So out of 4 sp3 hybrid orbital, only 2 will be forming sigma bond along with 1s orbital of hydrogen. That means you can see the presence of 2 lone pair of electrons over here. Okay, 2 lone pair of electrons are present. That means in water we can see 3 types of repulsion. One is between lone pair and lone pair. Next one is between lone pair and bond pair. And the last one is between bond pair and bond pair. Okay. In water, we can see the repulsion between lone pair, bond pair, and bond pair. We know that the magnitude of lone pair repulsion is stronger than lone pair, bond pair repulsion, which is stronger than bond pair repulsion. So the structure of water becomes V shape. You are getting, that is bell shape or V shape, with a bond angle of 104 degree 5 minutes. Is it clear? Due to the presence of 2 lone pair of electron, water possesses a V-shaped structure. That is a bell-shaped structure with a bond angle of 104 degree 5 minutes. Is it clear, children? sp3 hybridization with examples. So sp3 hybridization means it is the process of mixing of one s orbital with 3 p orbitals and forms 4 sp3 hybrid orbital. In normal case, the structure, the geometry should be tetrahedron with a bond angle of 109 degree 28 minutes. And we can see that in sp3 hybridization, the ratio of S character is very less. It is only 25%. Is it clear, children? So now we have to study about sp2 hybridization that we will do in next class. Thank you, children.